Hi folks, welcome to Unit 5, Lesson 5. So here we're going to take a look at question 1, and they're asking us to solve this equation. So first of all, this is what's known as a linear trigonometric equation, and that's because the exponent on the trig expression is 1, which means that we can isolate this trigonometric expression just using opposite operations, similar to what we do with linear equations. All right, clearly this can get more complex. We can have squares, we can have multiple trigonometric equations in trigonometric expressions in our equation. That's what we'll be looking at later on. Okay, but for now, we're going to start by isolating the trig expression. Because remember we said last lesson, we said that our goal is to end up with a single trigonometric expression equal to some number. So we can do that easily here by isolating sine of pi x plus 1. All right, so here I'm going to take the 3 to the other side, negative 3, and then divide by 5. So this is negative 3 over 5. And like we said, this is our goal, single trig expression equal to some number. Because once we have this scenario, we can do with what we did last class. Okay, it's just a little more complicated because our input is not just x, it's pi x plus 1. But I can determine one possible solution by using my inverse sine function. So if I take the inverse sine function of both sides of the equation, it's going to isolate the input here. It's going to give me pi x plus 1, and that's just going to be equal to my sine inverse function of negative 3 over 5. All right, now negative 3 over 5 clearly does not correspond to a special angle, so this is where we're going to use our calculator to approximate. And they're asking us to do decimal places anyways. So make sure your calculator's in radians. So inverse sine of negative 3 divided by 5. By the way, if your calculator doesn't automatically open up brackets, you should do it manually. All right, and we end up with negative 0.64. So here, this is negative 0.64. Now keep in mind, this was the answer not for x, but to the input pi x plus 1. Okay, but we know that the inverse sine function only gives us one particular solution. We can find a second solution, okay, by using an appropriate related angle identity. In this case here, since we're working with sine, I'm going to use the fact that sine of pi minus theta is equal to sine of theta. So that means another possible solution here. So pi x plus 1 could also be equal to pi minus, in this case here, our angle was negative 0.64. Okay, so in other words, that's going to end up being pi plus 0.64. So pi plus 0.64, and that gives us 3.78. Now, these are not the only two values of sine inverse, these are not the only two values with angles with a sine value of negative 3 over 5. We can keep adding 2 pi to each of these. But this is not how I'm going to solve the problem, because if I start adding 2 pi to 0.64, then when I'm looking for x and for each individual expression, I have to, subtract 1, divide by pi. For this one here, subtract 1, divide by pi, and all the future ones that come along. That could become very tedious. So we're going to look at another alternative. Is now that we have these two possible values for pi x plus 1, I'm going to solve for x. Okay, so now solving for x just means that we're subtracting 1, dividing by pi. So negative 0.64 minus 1 divided by pi. And let's see what that gives us. Okay, so negative 0.64 minus 1, then divided by pi. And that gives us negative 0.52. And then we're going to do the same thing here. To solve for x, I'm going to take 3.78, I'm going to subtract 1, divide by pi, and let's see what that gives us here. 3.78 minus 1, and then divided by pi, and 0.88. So these give us two actual values for the variable x. Now, how are we going to find the other answers that are going to come into play? Because these are only two of infinitely many values of x for which this is going to work. All right. Well, this is where we're going to use the periodicity of this trigonometric expression, but the period of sine of pi x plus 1 is no longer 2 pi because of this k value in front of the x. So let's figure out what the period of this expression is. Well, the period we know is just 2 pi divided by the k value, which in this case here is pi, so it's equal to 2. So when we want to generate further answers for x, we're going to keep adding multiples of the period. But as we said, in this case here, the period is not 2 pi anymore. The period is 2. So if I want to write all possible solutions for this equation, well, I'm going to start with this base solution, negative 0.52, and I'm going to add integer multiples of the period. In other words, I'm going to add 2n, where n can be any integer. And of course, the other set of answers which solve this equation will be this base answer, 0.88, okay, plus multiples of the period, where n is any integer. All right, so let's recap our strategy here. So step number 1 is to isolate the trig ratio. Okay, step number 2 is to use the inverse sine function to find one value whose sine is negative 3/5, and then our related angle identity, in this case here the one for sine, to find a second solution. Okay, step 3 is to isolate my variable if needed. In this case here, it wasn't just sine x, it was more complex, so I needed to solve for x. And then once I have my two basic solutions, I can just add multiples of the period. In this case here, the period is 2, to those two base answers. And this is going to produce all my possible answers. Okay, now just to show you that this works, we'll take a little trip to Desmos here. And I have it already prepared. So if you notice here, this is just the equation I have. So I need to determine when this expression is equal to 0, and that's what's nice about Desmos, is it shows me the x-intercepts. So if I look at this solution here, hey, that's that negative 0.52, our original answer. And then there we go. We did pi minus that answer, 0.88. Okay, I guess we're a little off because of the approximations that we did, okay, but very close. And then what did we do? We added, well, let's see what the period of this function is. It's not 2 pi, but it's 2. So we added 2 to find another answer. And now we're going to add 2 to this one. And we can add another 2. And you just can keep adding 2 to find all your answers, okay? So there's my negative 0.52, there's my 0.88. Now let's determine the answers specifically for the range from 0 to 6. Okay, so let's answer part B. So now that I have a specific range of values, well, I'm going to start determining based on these expressions. So first and foremost, I'm not going to take negative 0.52 because it is not in that range, okay? But I can take negative 0.52 plus 2. That'll bring me into the range. So that would be, I think that would be 1.48, okay? And then what am I going to do to find other answers? Well, I'm just going to add 2 to that. So 3.48, okay? And then I'm going to add another 2, 5.48. I'm not going to add another 2 because, well, it's going to be outside of the range of values that I'm looking for. So I get 3 answers from this first expression, okay? And then I'm going to do the same thing here. Well, I know I have 0.88, and I'm going to, again, add the period 2. So that's going to give me 2.88. And then I'm going to add 2 again. That's going to give me 4.88. And I'm not going to go any further because that's going to take me beyond 6. So my answers here are that x can equal to, let's put them in order, I suppose. So 0.88, then 1.48, 2.88, 3.48, then we've got 4.88 and 5.48. Okay, so in the end, there are 6 solutions within this range of values. Now, I don't think we should be too surprised because remember, the period of this trigonometric expression is equal to 2. So from 0 to 6, represents represents 3 cycles. And in each cycle, we should expect to get 2 answers from each cycle. And so 6 in all. So not so surprising. So let's go back to Desmos. Okay, so keep an eye on these numbers here, and let's check our answers. Well, we already saw the 0.88, and there's the 1.48, there's the 2.88, there's the 3.48, there's the 4.88, there's the 5.48, and of course these answers here fall beyond the range. All right, so to recap, and what we'll do is I'll take the notes for today, and let's do a recap as we're looking at the particular example. Okay, so let's take a look. Whoops, that's not what I wanted to do. Let's try that. And let's bring back the notes. Okay, so the algorithm for solving trigonometric equations. So step number 1 is isolate the trigonometric ratio. Now in this case here, it was very simple because it was a linear trigonometric equation, so we just had to use opposite operations. We'll talk later on about the more complex ones and the tools that you might use to isolate those trigonometric ratios. Okay. Step number 2 is to use the inverse trigonometric function, okay, to determine the first answer. Now notice here we're also talking about special angles. Okay. That means when we can find exact answers, we'll take a look at that next class. So that's what we did here. We used our inverse trig function to find one answer, and then we used the appropriate related angle identity to determine our second answer. All right. Next step, solve for the variable if needed. Notice I say if needed. If this was just sine x equals -3/5, x would already be isolated. In this case here, the input was not just x, so I had to isolate for it. Okay, and then the last step is to use the period of that trigonometric expression to determine further answers. In this case here, the period of this trigonometric expression was 2, so I just needed to add multiples of 2 to each of my 2 base answers to determine all possible answers. Okay, so now you're going to work on the next question, and the difference here is that the equation is not given to you, but you have to come up with a model first and then solve the equation. All right, so just to give you a heads up, all the equations in this lesson are linear trigonometric equations. So as you finish each example, you can watch the next videos if needed. Okay, that's it for now.